So in this case, I can define a delta x. The particle is within a finite region along the x-axis. And the only cost that it came at is I had to add many k values together, which means that delta k is now bigger than 0. We don't have a unique wave number anymore. And in fact, this gives us some plausible case where delta p, delta x is still going to satisfy the uncertainty principle. If I take the extreme case, and I really ask for the particle to be very localized, such that I barely even get one undulation, it becomes infinitely hard to define the wavelength here. Even as I get delta x to go closer and closer to 0. More generally, we add a large number of possible k values like so. Or if we had a continuous case where we wanted to integrate over all possible k's, it might look like this. This function a of k represents the amplitude at a particular value of k, and that's our sinusoidal wave, where this function ai represents the amplitude for a discrete value of ki. So for example, if a of k looked like this, in which I was going to accept all possible values of k at k0 minus delta k over 2 up to k0 plus delta k over 2. Then our net sine wave here would look something like this. In other words, that would be my wave function. This dotted line represents the envelope of the amplitude, and it's given by this piece. Sorry, that's an X right there. And this would be the more rapidly oscillating part with periodicity k0. Now, where's the actual particle? Well, if the amplitude here represents probability, we can say it's more localized in this area. The dotted envelope is moving with what's known as the group velocity. That's called the particle's speed. Another quantity called the phase velocity, which is just omega over k. This is the speed at which the inner sine wave is actually traveling along to the right. That's not physically meaningful because the dotted envelope kind of represents where is the actual particle location.